Okay, we are delighted to have our first speaker being Peter Caines. As we all may be aware, that he is one of the founders of the field with his paper along with Minyi Huang and Ronald Malhame back in 2006, really spawned this field, of course, simultaneously with Lars Leon's paper, which Pierre will be talking tomorrow. Peter Caines is the James McGill Professor and McDonald Chair at McGill University in the Department of Electrical and Computer Engineering. He's a highly decorated researcher, Fellow of the Royal Society of Canada, Fellow of the IEEE, SIAM, the Institute of Mathematics and its Applications, and the Canada Institute for Advanced Research. He also was given the Bode Lecture Prize in 2009 and has the Queen Elizabeth II Diamond Jubilee Medal for services to the community and to Canada. I'm sure that I have missed out many. These are just some of the highlights. And Peter Caines was not only the founder, but he continues to take the field in new directions. So we're really delighted, Peter, to have you talk about what he's currently working on, which is vertexons, graphons, and embedded Graphon Mean Field Game systems. Thank you, Peter. Over to you.
Thank you very much, Kavita. So first, my thanks to Kavita and Daniel for the kind invitation. My thanks to the organizers of the meeting. Kavita has covered the list there. We really owe them a lot. And please accept my apologies for not being able to be there in person. I really look forward to our in-person meetings in the future, or being at them. So without further ado, as they say, we'll launch into this, for us, new topic. So the title is Vertexons, Graphons, and Embedded GMFG Systems. And in the work which I'll present today, at various points, Rinel, Fogon, Hyundum, Xuangao, and Minyi Huang are implicated. And so I hope that I'll be able to point that out as we move through. I'll be, excuse me, I will be skipping, I think, for reasons of time, some sets of slides as we go through. So I hope that won't irritate people, but it'll certainly gives material that we can then return to. So the program is first networks and graphons, then Graphon Mean Field Game systems and GMFG equilibria. The topic of critical nodes, excuse me again, in LQG GMFG systems, their interpretation and an inconvenient truth. Then we have networks in space, the title topic of the talk, vertexons and embedded graphons, and then we return to what we hope points towards embedded GMFG systems. So the classical MFG model is such that key variables are simply averaged when, as a mass, they play a role in the behavior of the large population systems under consideration. So this is, if we think of the individual agents being distributed over the nodes of a large-scale network, then this corresponds to the network being completely connected and all the edges having equal weight. So this uniformity assumption often does not hold. So if we go to, for instance, to vivid graphics here, one is both concern air traffic. You can see that if you look at the intensity of connections between European airports within Europe, the Latin American airports, Asian airports, and Middle East, then locally you have very dense connections, but between these masses, clearly you have weaker connections or less frequent connections. Here, zooming in to the United States, you can see that if you take these cities, these are the airports of main airports in the United States, most frequently used. Again, you can see that the interactions are by no means uniform. Now, so this led us a few years ago to look at the use of graphons, and this is a very deep and useful mathematical notion, which was introduced by a group at Microsoft in Seattle and in Budapest about 20 years ago now, I think, and which is summarized in the magnificent monograph by Laszlo Lovic on large networks and large networks and graph limits. So here's the idea, that if you take a simple graph and actually simple in the technical sense as well, and draw its adjacency matrix with just whether connections exist or don't exist, with a 1 or a 0, or here in the pixel, a black entry or a white entry, then as you elaborate the network, you will get in the informal sense, a more and more dense pattern in the unit square. And indeed, it appears in this picture of the uniform attachment graph sequence that you have some form of smooth limit. Now, the uniform attachment graph is our base sort of workhorse of a non-trivial graph. And the way that you do it is that constructed iteratively, is that at each cycle, you take the nodes which you've already got in the graph at the n-1th cycle, you then bring in a new node and you attach it with probability 1 over n to each old of that is of the n-1 set of nodes. And amongst the old unattached pairs, you attach them with probability 1 over n. And then there's a random way of constructing this object. Now, that one thing to note right from the start here is that if you change the indexing of the nodes, you get a different picture. This is a fundamental issue here, and I'm sure you've realized that right away, that this it has a certain pattern, but if we change the numbering, in the indexing, would the pattern be different? The answer is definitely yes. So the base object of named a graphon is a limiting object, which is simply a bounded symmetric Lebesgue measurable function mapping the unit square into the unit interval. And it may be interpreted as a weighted undirected edge graph on the vertex set. So it's a limiting, you can regard it indeed as a limiting adjacency matrix. So the principal graphon spaces will be the mappings into 0, 1, but then you may want to have negative weights, in which case you'll map into, for instance, the interval -1 to +1. Okay, now a cut norm is defined in the following way, that we take our weighting matrix W, which we can actually call a graphon at this point by its definition, and then we take the supremum over the subsets M and T, the X and Y axis. And notice that if W is positive, of course, you just simply take in all the elements, but if W has got negative entries, or if you've done a subtraction, then this supremum is a non-trivial action. Now, so then, if we define a metric by re-indexing, if you have a difference between two graphons, then by re-indexing one of them with a class of measurable, measure-preserving bijections of the unit interval into itself. So you infimize over that set, and this then will give you the cut metric. There's also an L2 version of that, where you take the L2 difference and infimize over the very large family of measure-preserving bijections. Now, it turns out that the cut norm is bounded by the L2 norm, so the topology that's induced by the cut norm is going to be weaker than that in L2. And for the standard case, you could call it, where the infinity norm is bounded by 1, then you've got this relationship with the operator norm of W as an operator L2 to L2. So here's that picture again, and here's the basic result. That under the cut metric, the graphon spaces are for all such graphons and the cut metric, that the space of graphons is compact, where I is any closed interval, as we've just discussed. So this has a very significant consequence that if I take any infinite sequence of graphs, then there is a meaning that there will be one or more subsequential limit objects in this sense. So, so now we're going to employ the Graphon limit objects in our game MFG, in our mean field game analysis of large network of systems on large networks. So if we consider a finite population distributed over a finite graph GK, obviously that's going to be one of the graphs in our sequence. Then we're going to have a network of systems where each node will have a which we can call a cluster. Associated with a cluster is going to have a population of agents. So there's going to be a population of agents at each node in the system, and so the agents are going to have a state space, and with the state index xi. And notice I will range over the cluster members in the Lth cluster, and then as L ranges from 1 to mk, which is the number of clusters that you've got in the kth graph. Okay, so the total state space, which actually we won't use that much, but is worth realizing the system does have a total state, complete state, will be this, this direct sum of the states of the individual states in the individual clusters. So this gives a total number of states as the sum of the cardinality of the individual clusters. Right, so that would be when fine, that's good enough. Now, now we come to the dynamics. So there's going to be local, good old mean field dynamics, and then there's going to be the interaction of the dynamics between the nodes. So this is what we're going to, so here we have the familiar situation that at the ith node, that for the ith agent, so in the ith cluster, the dynamics will be defined, okay, for a typical agent. So we're sitting here, we're looking at this is the cluster associated with the ith agent, and J is the index of all the other agents in the same cluster, okay, in the same cluster. And so this is going to be the dynamical, this is going to be the drift influence term, in fact, that we're familiar with, normalized by the population in the cluster of the ith agent. So to read it. But there's also going to be influences coming in from all the other clusters, so that we're going to have the average of their dynamical influence, as would be seen locally, but then this will be transmitted through the network by, then this will simply be the graph link member. Okay, so this will be the element of the graph, which the edge weight before we get to any limits. So then the dynamics in the finite population, finite network situation for an agent I, okay, who will be a generic agent in the ith cluster, will be the local impact of the other guys in the ith cluster, then plus this average over the network of the edge weights of the drift influences in the other clusters, plus your individual noise, which will be a Brownian motion. Okay, so then I hope I can advance here. Okay, so let's move down. Good. Right, and then we're going to have costs, and again we're going to have the familiar cost term locally, but then there are going to be costs associated with the costs at which are located at the other cluster nodes. So then we've got the complete running costs, and we've got here, then we use the super tilde to indicate adding these together at the ith agent. So then this summary, so now if we go to the limit, so now let's go to infinite cluster limit, infinite graph limit, and infinite populations at each node. then at each node, we get the familiar mean field situation, assuming, of course, assuming that these exist. So this would be the state distribution of a typical agent, a generic agent alpha. And so this would be the local behavior. And then we've got the drift term, which is given by the average over, now we've gone to the limit graphon. Okay, so this is our graphon function value at alpha beta coordinates in the unit square. So then we're averaging, so hold alpha constant, average over all of the other nodes, so betas are running from 0 to 1. And at each node, we've got a measure sitting there, which we're assuming exists. This will be the local mean field, the mu beta at the betath node. Okay, so so what we have now is this. So this yields the complete local limit graphon drift dynamics given by the formula you see there, which is summarized in this way. And now notice the alpha agent, then it's going to be influenced by all of the mean fields at all of the other nodes. Right. So now, and here we've got our cost function for the infinite population. Now, assuming that these limits exist, so we go formally to the infinite population, infinite graph situation. Then we've got here what we call the Graphon Mean Field Game equations, which formally look very much like the familiar Hamilton-Jacobi-Bauman, Fokker-Planck-Kolmogorov pair. And in fact, we can also not necessarily have to assume that a density here exists. We can simply have the measure of the associated stochastic differential equation. And then, so then the situation then here is that we get the same conceptual formulation and problem that if a solution exists to this array, to this scheme, then we can interpret the alpha as being the Nash equilibrium value for a generic agent at its alpha, a generic agent at the node alpha. And alpha is going to range over, as you see, 0 to 1. So that will take us through the infinite set of nodes. And at each node, we're going to have a local mean field, here assumed to have a density P alpha. So this is to be interpreted as the mean field game problem generalized over the graphon. So, and then notice, how is it that what's going on at the other nodes gets into the action at any given node? Well, the answer is that it comes in through the role of the entire family of local mean fields coming into the drift and cost terms. So, and we will have an equilibrium for the Nash equilibrium for the reasons that. Now, the question is, does there exist a solution to this transfinite array of equations? And Migny and I then analyze the situation here. And the answer is subject, again, it's modeled on the standard MFG situation, subject to Lipschitz and control solvability conditions, there exists a unique Nash equilibrium solution to the GMFG equations. And this gives a best response feedback control strategy for each agent, depending, and then this is the key point, depending only on the agent's local state, and the family of Graphon mean fields. Okay, so we retrieve classical MFG problems of the MFG situation. In fact, there are two ways to do it. You can either take the network as flat, or you can say you simply disconnect everything and you get a continuum of problems, of classical MFG problems. Now the question, and I'm just trying to shift the bar here at the top of my screen so I can actually operate with this, excuse me for 1 second, get that out of the way. Right. And I hope that you can't see this, so I'll try to get that down here. The question is, how does it all connect with the finite problem that we motivated this? And the answer is, just as with the classical or standard mean field game problem, that we have an epsilon Nash result. And again, this appeared in this SIAM control optimization paper with Migny last year. Subject to additional conditions on the convergence of the system graphon. So that's the only additional conditions, but how the actual finite graphs converge on the limiting object. And the best response strategy, that if we follow the usual philosophy, namely we solve the infinite population, infinite graph equations, then in the finite setting, each agent applies the infinite population, infinite graph control, and in fact this gives rise to an epsilon Nash result, in the sense that for every epsilon there's going to be a population size such that for all larger populations, a unilateral move by an agent using all possible past adapted information, so this is information used in a causal manner with observations on all the other states at all the other nodes, can only gain epsilon worth of value. So this is what connects one back to the finite setting. Now, let me just, there's one sentence here which I want to explicate, where it says solvability conditions. So what that means is that this infimization of the Hamiltonian is a well-defined operation, giving a unique, appropriately measurable control. The next step in the program is to follow an idea which was introduced by Renel Fougon-Chondam, which is the idea of critical nodes. So we'll illustrate this with a simple example. So we take a univariate linear stochastic differential equation that's given in 16. And this is at the alphath node. And that you'll notice there are no mean field dynamics in the local equation, the agent. Now, the mean field business comes in on equation 17, where the objective, just as in the base problems of mean field games, the problem for the alpha agent is to track the mean field, but this isn't just the mean field of the local population. In fact, what this is going to be is this graphon averaged, in fact, mean of the mean field at all the other nodes. Notice the states are scalar, and we've got a continuum of nodes. So with this base problem, as we know that what this reduces to is to solving a stochastic control problem, the key move of mean field games, that you solve a stochastic control problem against the mass mean field. So this is the standard setup where we've got here the, as I said, the mass means the global mean field coming in, but it's integrated, and then this is what you have to deal with locally. And then assuming that we can solve the that we then proceed, the solution procedure involves solving the consistency conditions effectively, and then that results in the solution with which we're familiar. Now, the definition of critical nodes to begin with is that it's a stationary value with respect to the index, with respect to the agent index of the mean field seen locally. So it's as we said before, this is going to be the phrase we use was the global mean field term. So I'm going to use that term here, global mean field term. So it's possible then to actually, in these two simple examples, to characterize the critical nodes. Now you can regard those as being, these could be best or worst, but certainly that these are, if they're interior to the unit interval, these are going to be nodes at which locally it's going to be a stationary value. So depending, of course, on the second derivative, it could be locally best or locally worst to reside. So if you're entering the system as a fresh agent, you can, and you've got to decide where in this infinite mass of agents and nodes you want to place yourself, you would look for the critical node. So we regard this as well motivated. Okay, so what happens with the Atelier graph, which is flat? Well, then it's very simple to see that you see the Graphon integration vanishes, and so in fact it's not dependent upon your local node. And so in this situation, the Atelier graph, that all nodes are critical nodes. Now, a more interesting situation is the uniform attachment graphon, which you'll recall from earlier. And then in that case, the graphon has the formula 1 minus max alpha beta for alpha and beta ranging over the unit square. So apart from a ridge down the middle, this is smooth. And the what one gets is that the global mean field is given by this formula, which clearly does depend upon alpha, the alpha index of the agent. So and I reiterate, this is in work with Rinel Chendom and Rinel Fogon-Chendom and Minyi Huang, and it was appeared at the CDC last year. So here, if differentiating with respect to alpha, you can see that the corner node alpha equals 0 is a critical node. Okay, so that's admittedly a boundary node, but it's a well-defined notion is that that either for the best or worst behavior, you'll place yourself at the root of a uniform attachment graphon. This goes on, and we can then go to, it turns out that with that definition of a critical node, the controls are also stationary with respect to your alpha index, and indeed your Nash value will be stationary with respect to alpha if the node is critical by the definition we've just given. Now, in fact, henceforth, we take the more general notion that the stationarity of the value function at a node is what will define the notion of criticality. Okay. Right. So now, however, there's a problem. There's what we call an inconvenient truth, which is that Graphon Mean Field Games and control have been carried out within the standard framework of graphon theory, which we sketched at the beginning. Hence, the nodes of any finite graph under consideration are indexed by intervals of real numbers lying in the unit interval, and the limit objects by real numbers in the infinite graph limit. Further, in the definition of the cut metric, the unit interval or subsets in the simple case you've seen, or even in more general presentations, you can give references, that the indices in the definition of the norm and hence of the metric are subject to measure preserving bijections. In fact, a full version of a graphon, a complete version of the notion of a graphon, is that it's an equivalence class of objects subject to measure preserving bijections, and that's the limit notion of the fact that when we started with our description of adjacency matrices, that we could have just as well have permuted the indices, and we would have got an equally valid object. So for this reason, there is in general no geometric significance to the value of a parameter, which is used to index any particular node. And as we've seen that, and you can quickly convince yourself of that with any planar graph. Consequently, if two nodes of a graphon are embedded in Rn for n greater than or equal to 2, And if they've got approximately equal indices by chance, and excuse me, so if two nodes on a graphon are very close in their indices, there's no reason to believe that they're close back in Rn on the graph from which they originated. So, in fact, more specifically, any attempt to code a subset of the elements of a limiting infinite graph embedded as an open subset in Rn for n grading 2 by the elements of the unit interval in a continuous and continuously invertible manner must fail. And this is due to the non-existence of homeomorphisms between open subsets of Euclidean spaces of different dimensions. And hence, in particular, we're not going to have diffeomorphisms. And so this has the consequence that with the possible exception of graphs embedded in R1, there's no standard meaning, such as variation with respect to location, that could be given to the differentiation functions with respect to the node alpha. So in response to this, assuming that one is motivated to look for critical nodes and that one wants to differentiate Nash value functions with respect to the parameterization, some parameterization of the graph, so we introduced the framework of embedded vertexons and embedded graphons, from which we define a notion of differentiation with respect to node location. So this, our beginning efforts here is intended to have particular application to geometrically situated graphs. There's no contention here that graphs are typically geometrically situated. But if you think of the airport diagrams that you saw, airport connections, and the air traffic flows that you saw earlier, then indeed this is strongly motivated. Other situations where the indices correspond perhaps to social insurance numbers, or just simply the numbers of people's bank accounts, preferably not interlinked to each other, then you'll have essentially no geometric interpretation. So in our program today, the next step is what networks in space, vertexons, and embedded graphons. Okay, and the co-authors of the previous part of the talk bear no blame or responsibility for this part, although I've had a lot of stimulating discussions. So. So now let's take, what we're going to do is embed our graphs in the unit cube. Now, so this, to do this, one wants to think of zooming in and zooming out. This isn't quite as preposterous as it looks, because of course we were looking at an air traffic flow graph of the United States on a picture the size of the laptops or screens that you're looking at. So we're going to think of Vn is going to be a graph embedded in the M cube, and En will be the set of edges. Now, of course, one immediately pictures these as one-dimensional subsets, lines of the unit cube, but of course, they're in their indices, they're going to fall in Vn cross Vn. And we're going to give them weights, whereas between 0 and 1, and the 0 weight will be the non-existence of an edge. Now, a key point in the construction is that of lattice equipartitions. This isn't a standard name, but what we're interested in doing is constructing hierarchies of finer and finer partitions of the unit cube. So the base one that we'll think of is going to be given with edge lengths of 1/2 to the k plus 1, with k running through the indices. And so then you need, of course, multi-indices to actually indicate a particular cube, a particular voxel in the unit cube. Now, this isn't a misprint. This here, that the double parenthesis is open in case you're basically your edge is inside, and it's going to and it'll be closed if one of your edges on the boundary, so that'll close that edge. So these are going to be disjoint voxels, all non-empty, whose pairwise disjoint, whose union is the whole cube, and so indeed it is a partition. And we're going to write PL less than equal to PS, where L and S are integers. This is read as PS, notice higher up the refined PL, which will be coarser. Now, we're actually, we will invoke the notion, but it's not really critical to understanding what we're going to say next, of a uniformly asymptotically dense partition hierarchy. So basically, that's all partition hierarchies that behave like the lattice hierarchies with the rectangular edges. So for each K, the cells will form are required to be convex subsets of M, and that QK itself is a partition of M. So that's just a partition with convex cells. As we increase the index, then we're going to refine. So we're going to be refining. So notice as the indices go up, we're refining. So the cell size is going to be going down. So that's our second requirement, which is quite straightforward. But then we want this asymptotically dense notion, which I'm not going to go into here, which is which we phrase in the following way: that any telescoping sequence of cells of our particular member of this of the uniformly asymptotic family. So pick one, and then we can take a telescoping sequence, and if such that any such telescoping sequence with infinite intersections of point, then that sequence must be interleaved, not necessarily n to n plus 1, but interleaved by a sequence of cells in the hierarchy P, and vice versa. So this means that it refines and is mutually refined by the lattice hierarchy. So now here's the key definition. So a vertexon consists of a vertex set, so it's just a bunch of points in the unit cube, a vertex set of cardinality Vn, not necessarily equal to n, lying in the cube, together with one chosen uniformly asymptotically dense partition hierarchy member. So think of that as just being the rectangular lattice, guys, and then we don't really need to think about all the other possibilities. Then a vertexon sequence, or VQ infinity, or suppressing that just V infinity, is a sequence of vertexons associated to some partition hierarchy. So all you do there is simply that you're moving along, you've chosen your partition hierarchy, and then you're moving along the sequence of vertices. Now, the situation we always think of is that you're putting in more and more and more points as you go along. Okay, you can think of the cardinality of Vn being n, and then at each step you put in another point. Okay, so then you're adding vertices, and of course the edges of the graph, which are of which go with it. So now we define the Voxel stepping functions, and these are inspired directly by stepping functions in the Lovesh proof of the Graphon convergence theorem, Graphon compactness theorem, which inspires this proof pattern, where we go to the kth level of the partition hierarchy, that we go to the hierarchy to the partition pk, and then on the cell, so the ith underbar cell of pk, and we see how many elements of Vn fall in it. Okay. Now the cardinality has to be greater than or equal to 1, so this isn't going to be infinite here, this ratio. But if we forget the measure for a moment, this is the ratio of the number of vertices of the total that falls in the ith cell of the kth level partition hierarchy partition member. partition hierarchy member. So we're in the partition PK, we look at this particular cell, and and then we see what fraction of the vertices fall in it. And we of course do that for all of the voxels, cells, voxels. Okay. So so this is going to be a fraction, okay, which is going to be between 0 and 1, and then we're dividing by the volume of the voxel. Now there's something which I call the Dune Lemma, because we saw how to do this. I saw how to do this when we were watching the Dune movie. So the thing is that there's an averaging property to the vertexon stepping functions, which is analogous to the Tower property of conditional expectations. So what this says is, you see, L is the coarse member, is a coarser lattice, then it's refinement PS. So PL is coarse, PS is fine. So what it says is that if you average over the coarse partition cell I, the values, you average the values of the voxel vertexon stepping function values at the fine level, then the value you get over the coarse cell will be equal to what you would have got had you simply gone straight to the coarse cell and computed the value of the stepping function there. So it's just like the Tower property of conditional probabilities. What's more, if you run n to the, if it is the case that these guys are converging in L1 to a limit u infinity as the sequence, then this averaging property holds for the infinite vertices limit. Right. So here's the picture, and with picture credits to grateful to Xuan Gao. I've had many cheerful disputations about this subject. And so here you see we're running along the kth level partition here, just two by two partitions, and we've got our fixed set of points, and then you see that sorry, we have that it's going to be fixed in the sense of comparison with the next row, and then here we're looking at the fraction. We're looking at how the as we we're holding the cells constant and we're putting in more points, and what's going to happen is that these levels are going to have subsequential limits as we put in more and more elements, and that's just a consequence of Heine-Borel in each box, and then done over the set of voxel boxes. Okay, so it's Heine-Borel that way to give you a limit with infinite number of vertices. And you do that for each level. So here it is with 4 by 4, and you can see here now that you see that the number of steppings remains the same, but the values are changing as we put in more and more points. Okay, so that's the key picture. So then the theorem, so I'm going to speed up a bit now, so then the theorem is that if we consider a sequence of vertexons with associated vertexon function sequences, then the first, we can just use the pictures. First is the claim that there are convergent subsequences going along as we put in more vertices, as we hold the partitions constant. Then the next move is that if you consider the right-hand end limit functions, that in fact they converge as you refine the partitions, and that's a consequence of the Martingale convergence theorem by a beautiful move in the proof of the compactness of Graphon spaces in the also Lovish text. What's more, you can take a diagonal sequence, so you can actually run along UNKs that then converge to the limit you identified at the second step here. Okay, so then when it comes to the family of uniformly asymptotically dense partition hierarchy members, that if you've got an R and an S partition hierarchy and they have unique limits, then those limits must be the same. So in that sense, we're partition independent. And here's a picture again, more points, one level, more points, one level, take the limit on the right-hand end with infinite points, and it works for finite points as well, and then you get your limit vertexon. Now, so then I'm going to speed through. If you take a finite set of points and you carry out this procedure, then actually what you end up with will be an infinite spike on the finite set. And so the limit is equivalent, is in the equivalence class of 0, L at 1 functions. I was shocked to find out that if you put if you do the same procedure but at the points 1 over n, 1 over n, okay, so you're filling in points in the unit square at 1 over n points, then you end up with a unit mass delta function at the origin, okay? So if we, again, I will speed up now, if you actually create your vertexon by sampling on M from a piecewise continuous density, then what you get by writing out the formula using the law of large numbers, then actually what you get locally will be just what you hope, namely that almost everywhere you're going to get the density which we assumed at the beginning, piecewise continuous density, which at the beginning we assumed existed. Bueno. Now, if you do this with the uniform, so the next thing is to you're going to be asking, well, yes, but where is the graphon? You know, what we've got here is bunches of points. But the key feature here is that you want to be able to differentiate, so you need to move around in the limit vertexon object. Okay, so even before you've actually put your graph there, first you need a limit object that you can locally, where if you plop down in it, you've got an open set where you can actually make for instance, you can differentiate locally. So that the next key feature is to separate out the construction of the vertexons with the construction of the embedded graphons. So stepping through, the point is that what we're going to do is do these two operations simultaneously. So an R2M embedded graphon is going to be a positive L1 measurable 0,1 valued function on the 2m dimensional unit cube. So this is simply going up in the dimension of the standard situation. So in the standard situation, m is equal to 1, and you've got the classical graphon setting, okay? But we want stuff in space. Well, stuff in space. So the graph was sitting there in m-dimensional space. So the graphon is going to be defined in 2m-dimensional space. So then we rerun the construction. So now we do edge voxel stepping functions, which are defined counting the number of edges, actually with weights if you wish, between the vertices in the voxel pki and the voxel pkj. So in fact, you see the voxels in the R2M setup are going to be the product of all possible voxels in the m-dimensional setup. And notice here that the possible number of links will be cards squared vn minus the diagonal. Okay, now you run through the same argument essentially, but we start off on our vertexon on our VN-EN sequence. You start off along the sequence that has converged to one of the limits you know exists for the vertexon. So you've chosen that sequence, and then you repeat this row and column argument that you saw just now for the vertexons. Repeat that for the edge stepping functions, and then that gives us a double limit object, so that we then have a sequence such that the stepping functions for the vertices and for the edges will jointly converge to a function on m cross m squared. Okay, so, and we have the same uniqueness result. So to start with, with this new setup, quite frankly, we're still investigating it, which is kind of exciting. And the first simple case is if you take an Erdős-Rényi type randomly placed vertices, and then you connect, so then you put in your vertices in uniformly over the unit interval, and then you assign edges, okay, but you're going to do it in the square, not the unit interval, so I misspoke there. Okay, so you're going to put in your vertices on the unit square uniformly, uniformly randomly chosen, then you're going to assign edges with probability in the standard Erdős-Rényi way. So then what happens to the limit vertexon function simply takes value 1 on the unit square, and then the corresponding embedded graphon in the 4-dimensional space will have the intensity P throughout the cube. So now we've got our two limit objects, both of course not particularly complicated functions, both are flat, one value 1, one value P. Okay. Now here's a negative example. Now I know that, Daniel and Agathe have been working on sparse networks, where which have got a certain uniformity, a certain shift in variance. We'll take the simplest possible situation there. If you take the grid lines of a checkerboard on the square, and then and you put in n squared points, just arrange them at the intersections of the edges, and then you do the vertexon limit move, what you end up is with a unit density on the unit square. Okay. However, in 4 space, the embedded graphon will be a set with an empty interior in the 4 cube, which in fact, of course, vividly communicates the sparseness of the network. So of course, so this is really intriguing because whereas in the vertexon, they're going to have open sets in which you can in principle do differentiation, it's meaningful to make a move, that actually is not going to correspond to a move along an edge unless it's in a rectangle in a direction parallel to the cell boundaries. So we're still trying to understand that. Now, to come to an example that we haven't figured out yet, suppose that we take any density in the unit square as we over the unit cube, and then we actually connect the points in the unit cube using the uniform attachment graph. So then we're pretty sure that we're going to get an object for instance, the fourth dimensional cube, 4-dimensional cube, that will have a non-empty interior, but we don't know what it is yet. Okay, back to the GMFG setup. This means here are the same equations again. This is the GMFG array, right? But now you see, if it's the case that the alpha is the parameterization of a node where the vertexon has got strict, what it calls is got a strict support. I mean, the sets where it's actually positive, that set is open, then you can actually meaningfully differentiate this object locally. You can well, if it's smooth, you can actually define smoothness first off. So you have a possibility of defining differentiation. Certainly you can define continuity and so on. And then also we can relate that to the graphon itself, if that has similarly got a non-trivial open interior. Now, so the conclusion, and I'm just going to jump through to a feature as the time is running out, we actually get for free the notion of node density, because you see that the vertexon function actually will be defined on the M cube, and so you can take the graphon function and multiply it by the vertexon value, and that could have a real meaning, modeling meaning, because that could be, for instance, like the density of the cities in a geographical layout before you actually consider the asymptotically infinite populations in each city in order to do a GMFG analysis. So, So we haven't investigated this yet, but there's this really interesting modification of the definition of the Graphon function in the GMFG setup. So the conclusion is that a framework is proposed here, obviously just beginning, for developing an embedded Graphon Mean Field Game theory if you're in a situation that the distribution in space of agent-inhabited nodes is of significance, and the connectivity of the nodes as a function of position in space is of significance. And then this permits the application, subject to hypotheses, of the differential calculus to quantities in EMFG system. So this is now embedded graph. That should be EGEMFG. The letters are piling up a bit here. EGMFG systems, which are functions of location. And of course, in particular, maxima, minima, saddle points of mean field game equilibria. And that brings me back to my last slide. Okay, so that's the state of play so far. And thank you very much for your attention.
Okay, okay, I'd like to see if there are any questions here in the room first. Yes.
Thank you, Peter. Very nice talk. Lots to think about, as always. I'm trying to wrap my head around this last part of the talk on these embedded graphons, and I'm wondering if you can kind of summarize like what you're kind of modeling a graph in space rather than just modeling a space itself. I'm wondering like what information would be lost if you just assumed your continuum model was, a manifold of some sort. So then you can differentiate, of course, but it seems here you have a bit more information to play with.
Okay, the embedded manifold would come along with the problem. I should say, when I first started to write this down, I started on a Riemannian manifold, and that seemed to give too much of a transition hurdle to people I was trying to explain it to. That was a barrier, and so I thought, no, I'll just start in the unit cube. So, for instance, if we take, and I'm not quite sure how quickly we can get back to it, but if we just take our maps of the maps of the air, for instance, actually that forms quite a good example. That if we go back to our motivating pictures, if I can get back to it in real time, here that if we're using it's typical to look at a map of the United States on the plane, or any smaller geographic location. So putting that into the unit square, of course, zooming out appropriately is reasonable. But actually, if you go to the first one, which is supposed to be planetary, you would want to put that to begin with on the sphere, for instance. So one's not constrained in terms of the embedding space, but you do want it to be a metric space. And then the vertexons would be here. So they would be the actual limit blobs, okay? And then in the product space, you'll have the connections themselves. So it's lifting the classic Graphon 0,1 and 0,1 squared framework into m dimensions, or putting it onto a Riemannian manifold.
Okay, but there's not a priori a connection between the geometry and the graphon, though. There can be, but there's not necessarily.
Oh yeah, actually, you're quite right. The answer is no. There is not a connection, because you can simply. That's right. It may come later. There may be an intrinsic curvature defined. That's possible. I haven't investigated that yet. Speculated upon it. But as you see here with this picture, that the graph object that you get, just as with the graphon, can vary completely with just how the connections go, But we've got two things going here. One is the geometry of the limit node set, and then there's the geometry of the limit edge set, and they can be in different places, of course. I hope that was an attempt at a plausible answer to your question.
Oh, very helpful. Thank you. Thank you.
It's actually just following up on that. So do you have an example like of a concrete where there's a different geometry for the edge and the vertex sets that you had in mind? In particular, I mean, of course, your framework allows for it.
Yeah, a different geometry. The point is that, to be perfectly frank, we're still working on good examples, because
sure.
this is really new stuff. So the simplest example worked, but of course it's quite uninteresting, which is where we have there is the following situation that the geometry isn't really different, but you see. Let me just see if I can get to that's not a negative example. Yeah, the Edo-Schrenier situation is that your distribution of vertices in the unit square need not be uniform. You see that it could, for instance, be Gaussian. It could be renormalized. It could be as we had before. You see, when we did our construction, it was any density, but still on the unit square. Okay. Then the edge function itself is going to be, I think, constant, but be careful. I don't want to make a simple mistake there. So, okay, this is a very simple concrete case that I think the first really non-trivial interesting case will be when we actually take, this is the negative sparse case, where we take a simple distribution in say the M cube, and then the connections are going to be according to the uniform attachment graph sequence. And to be perfectly frank, couldn't work that, didn't have time to work that one out this talk.
Sure.
Depends what you mean by geometry. The embedding spaces so far are just good old-fashioned cubes in Euclidean space, the M cube and the 2M cube. So I don't want to say more than that because that's what we've got so far.
Okay, thank you so much. Are there any other questions in the room? If not, are there any questions from the virtual participants?
Virtual.
You could either unmute and talk, or you could, I don't see anything in the chat. If not, it's also 10:30. So we're really very, very grateful for Peter for this very thought-provoking new direction. Let's thank Peter once again for a wonderful talk.